Good morning, everyone. Can you all hear me? Can you see my slides? Anyone out there?
Yes.
Okay, fine. Now, we have had a bit of a brief introduction about steel design last week. So let us continue from there. Now, if you look at yes, my image will not be very clear thanks to my webcam, which is not very clear. But don't worry about it. It may get better, or at least you know that I'm here. So there are some images appearing. So now, if you want to understand now the zero code 3, which is the fundamental document or the basic document that we are going to use to refer designing of various structures. Now, so far you have learned how to analyze a structure. Analysis means that, okay, you determine the loads. Even sometimes you may not have learned about how to determine the loads acting on an element. Say, if you consider a beam, you would have been given some loads on a beam and you were asked to analyze and plot shear force, bending moment, axial force diagrams. But you may not know how these loads were derived, because these loads are derived from actual situations. So I think as part of the previous section of this module, you would have learned about how to derive the loads. So if you look at the Euro code that is adopted in Sri Lanka as well, so Sri Lanka Standards Institution adopted Euro code as the code of practice in Sri Lanka as well. So if you look at the Euro code has two components. It has the code and it has the national annex. So the national annex differs from country to country. So the national annex has country specific details or specifications that are required when you consider design of a building. So far we don't have a national annex. They are developing a national annex for Sri Lanka, but we have adopted the main code, Euro code. So in the future, Euro code will be used for any designs in Sri Lanka as well. The reason the Euro code is used because Euro code provides a comprehensive design guideline, and also it provides a lot of flexibility for a designer to choose parameters that influence the design. Now there are several codes available. There are about 9 codes are there, and each for different design purposes. We are very much focused on EC3 or Euro Code 3, which specifies how steel structures can be designed. What are the parameters should be considered when designing steel structures? Now, to say this is the Euro code, and has been feeded. It is being feeded by several other codes, so it cannot stand alone on its own, and it requires data, or it requires some design specifications from other codes as well. So if you look at the EC0, that is Euro code 1990. So 1990 specifies load combinations and factors. So in a situation, in a building or in a structure, you might see there are several different types of loads can be expected on a structure. Its own weight, we call it as a permanent action. The weight or the load applied due to the use of the building, we call it as variable action. And then you have wind actions, you have snow actions, you have earthquake loads. So there are different types of loads. So this Euro Code 0 gives you a basic of how these different loads can be combined. Say, you might anticipate a day where you might have the permanent action, which is always there, and you might experience live or variable action, and it could be a windy day with some earthquake. So you may have all 4 loads acting on a specific day. But in generally, say if you take the building, the engineering faculty building, about say half of the time the building experience only the self-weight. Then the another half of the time it experience self-weight plus variable action and wind action. So the probability of these all possible forces acting on a one day could be very less, the probability. But when designing a building, we have to consider these probabilities as well. Okay, so we need to consider how can we incorporate these possibilities. So Code 0 gives us pretty much how to decide these combinations. And there are several factors that we consider when designing a when we consider the loads. So there are material specific factors and there are load specific factors. We have seen a few last week. So if I go through, take you back, say these are partial safety factors of materials. So these factors uh, and uh, and there are the load specific factors here in the table below. You can see the ultimate limit state, service limit state, the factors. So these factors are discussed in detail in Code 0. Then you have Code 1. This is where we obtain the loads. Say if it is a concrete building, and what is the density of the concrete should we consider when calculating the loads. What would be the variable action on a classroom? What would be the variable action on a shopping mall? So these values, say you need to choose a value to determine those loads. You can't arbitrarily take a value, because if you arbitrarily take a value, then you are liable for that assumption. And if you have used uh, the values given in Code 1, your liability is less. So you transfer the liability to the code. So even if you design a building according to Code, considering all the loads and combinations and partial factors, if there is a issue on the building due to the loads, then you can know that or the liability of that issue relying on the code, not your design, because you have designed according to the code. So the code gives you the protection, so it takes some liability. So that's why we need to follow strictly the codes when designing a structure. So now Code 1 for loads and Code 3 for steel structures, Code 2 for concrete structures. Even we might need some data from concrete structures to design uh, composite structures, which involves steel and concrete. So Code 4 for composite structures. Then you have further codes about materials, say concrete materials, BSCN 2 and 206. Concrete execution, BSCN 13670. Reinforcement specifications are given in BSCN 10,080, and steel execution specifications are given 10,090. Steel materials are discussed in BSCN 10,025, 10,210, and 10,219. So every detail, say if you want to use a steel, okay, the steel should be according to the code, then you go and refer the steel materials code. If you want to design, if you want to consider a load for your design, then you go and check the Code 1 for the loads. If you want to consider different load combinations, you go and check Code 0. So you may have to use all these codes even when designing a steel structure. So you may not be confined to one code, because you need to have some idea about how to use other codes. So if you look at the next slide, where we mentioned about structural classification of steel section. Now, why we are considering this classification of steel section is Now let's look at this. Uh, so let me take a paper. Okay, so now let me tell you why we need the sections. Okay, now this is a situation. Uh, okay, steel design. Ninth week. Now, for example, let's take a building. A building. So I'm going to assume a very small building. Say we have a two-story building. Say a shop. So here we have the foundation. Okay, so the building. Now the building has uh, beam. So there are four beams at the top. Then you have a column. Then you have a slab. So slab here. Then you have foundation. Okay. So now, if you want to design this building, you need to design uh, slabs, beams, and columns and footing. Okay. So now that is how we have to design. Okay. Now when we have to design this, we don't know the what we don't know is what we do not know. Uh, we don't know the slab thickness. Even if we assume concrete slab. So even it could be a concrete slab, but we don't know the slab thickness, and we don't know the beam breadth and depth. So the breadth and depth are, this is B, this is D, and there'll be a section, a steel section. Then uh, we don't know the column section. So if you take a column, there'll be a section like this. This is, just an example, okay? But in steel, it will be different. Uh, Footing, we don't know the depth of the uh, footing. We don't know the type of the footing. And we don't know the load transfer mechanism of the footing. Okay, so these things we don't know. And if you want to know this, or if you want to, You can't find them from somewhere. What you need to do is you need to do the design calculation. So you have to determine these values. You have to determine the slab thickness. You have to determine the breadth and depth of the beam. You have to determine the cross section of the beam column. You have to determine where would be the depth of the foundation, what would be the type of foundation, and how the load is transferred from the foundation to the soil. So we don't know that. So you have to determine that. So in order to determine that, you need to know the loads. Okay. So to start with, you need to estimate the loads acting on the building. Okay, so you need to estimate the load acting on the building. To estimate the load acting on the building, say there are different types of loads. So you have permanent action, you have variable, wind, earthquake. Okay, so there are 4 different types of loads. Now, how to determine the permanent action? So permanent action is about the self weight of the building. So if you look at the slab or a beam or a column or a foundation, let's leave the foundation aside, because once we complete all the column designs, we can come to the foundation design. So basically, slab, beam and column, we don't know the sections. So without knowing a section, you can't uh, find the uh, permanent actions, that is sulfate. So how to get the sulfate? Uh, we can get the sulfate from the code. Let me so if you take design, okay, let me take the course. Okay, so now here we have I think these are available. I'll tell you where to look at. Say hot rolled section tables. Okay, so hot rolled section tables give you the sections that are commonly available sections that we can use for the design. So uh, where you can look for them, uh, there is a uh, uh, you can search for uh, Tata Steel Blue Book. I think it's no longer Tata. Maybe Tata sold that one. Anyway, earlier it's called Chorus. Okay, so Chorus Steel sections Blue Book. So if you search, you might find them. And this, or you can also look as Tata Steel Blue Book. So that is a table that consists of tables, set of tables, all the sections that are available in the market. So now if you take beams, so these are the options we have that are available for beams. So here there is, say if you look at this 1016 305 487 means now it has a mass of 486.7, roughly 487 kilogram per meter. The depth of the section is 1036. Width of the section is 308.5, and the thickness and all. So basically these two values indicate roughly the depth and the width of the section. The third value indicate the weight of the section. So if you look at further down something, say if you look at this one 838292226. So here this is the depth. This value is breadth. This value is the weight per unit length. So these are the values, these are the different sections available in the market. So, and this table consists all the values. Say it consists the thickness of the web. So web means, let me show you. Say this is the breadth, this is the depth. This top element, these elements are called web, sorry, flange, and this is the web. So if you take an I section, say if you take an I section, normally hot roll steel beams are I sections. So this is called flange, top flange, bottom flange, and this is called web. So in the steel book, you have the depth of the section marked by H, width, breadth marked by B, thickness of the web, thickness of the flange, root radius R. Root radius is this element is called root radius, that is R. The radius of the fillet is called root radius. The depth between the fillets is given by this. So the depth between the fillets. So here this is the root radius. Then if you remove the root radius, then there will be the depth between the fillets. Okay. So those are the values, and then it has the radius of gyration, second moment of area, plastic modulus, elastic modulus, all the required data for a steel section is available on this Tata Steel Blue Book. And the one I am using is a bit old. I think it has been updated. So this is the Society of Structural Engineers produced this structural engineers pocket book, 4 codes. So so now when it comes to the permanent action, if you want to know the weight of a beam, say if you are designing a beam, weight of a beam, you can obtain from the steel book. Or if you want to obtain weight of a column, again in the Tata Steel Blue Book, you can obtain the values. So here UK beams, then UK columns. So this is UC or UKC, it's marked by. Then here you know you have the values of a column, same as the beam. Okay, so you can obtain the sulfates from these documents, from this table, only if you assume a rough section. So generally, as a structural engineers, through practice, we might be able to, you know, approximately assume a section. So when it comes to the permanent, determining the permanent action, first we assume a section. So we assume through experience. And whether it is a slab, say even if it's a slab, you can assume normally slab thickness in the range of 100 millimeter to 150 millimeter. Generally 90% they are between 100 millimeter to 150 millimeter. So depending on the purpose and the span, say if you say if we have this building is about say 6 meter and 4 meter, 6 meter length, 4 meter width. So we can assume a slab thickness of 125 millimeter. So if we assume 125, say um, permanent action, say slab. So you assume a thickness 5 millimeter. So for this building, we assume a thickness of 125 millimeter. Then you have to go through the concrete design procedure to see whether the slab is suitable to carry the load. Actually, that design, the slab design, is not within the scope of our learning here. So we will not be looking into detail about the slab design. But let's see, this is I just want to tell you the procedure. So we assume 125 millimeter, and we check whether this slab can carry the required load. So how to do the load, say required loads for slab. Say if it is a 125 millimeter thick slab, so normally the reinforced concrete density, okay, forced concrete density from Euro code 0. Say let's see, we will check Euro code 0. uh, I have Euro code 0 here. So Euro code 0, okay, so Euro code 0. So Euro code 0 gives the basis of structure design, right? So which I mean, now say for example, if you want to determine the reinforced concrete density, which code should I refer? Euro code 0 or Euro code 1? Anyone who is listening can answer. Which code should I go and refer? Euro code 0 or Euro code 1? Okay, so let me uh, Let me do a quick survey. Okay, so I'll uh, which hero code is to determine slab self-weight of the slab. Hero code 1. Hero code 0. Okay, so I'll share this one so you can tell me which one. So uh, you have to go to this website called www.menti.com. So that's where we can conduct a little survey. So you have to go to www.menti.com and go there, and you have to use a code 3771894. 3771894, and you can choose one of those three options. Okay, so let me see how many of you are going to use that. So it's here. You have to go to the www.menti.com and use the code 3771894 and tell me which code we have to use to determine the self-weight of the concrete slab. So uh, if you assume a thickness 125 millimeter, you can find the self-weight of the slab. Then the variable action, the load acting on the slab, we have to choose that. Okay, so it's depending on the purpose of the building. So I earlier told this building is going to be a shop. So if it is a shop, what's going to be the variable action? So again, we need to go and see the variable action that acts on this building. So let's say if I go to the code 1, where I can find actions on structures, and uh, I can look for what should be my load. So it is depending on the purpose of the building. Say if it is a type A category building, means it's areas for domestic and residential activities. So if you are designing a house, your category A for variable action. If you are designing an office, your category B. Areas where people may congregate, that is, if it is a cafe, restaurant, dining halls, reading receptions, C1. Churches, theaters, and waiting rooms, lecture halls, C2. Museums, exhibition rooms, etc., C3. Dance halls, gymnastic rooms, C4. And areas susceptible to large crowds, C5. Then shopping areas, D1 for retail shops and D2 for department stores. So department stores are like big supermarkets like Pico, Kiehl's and all. So we have to decide. So now in our case it's D1, it's a retail shop. So what's the load for D1? So D1, the distributor, if you assume a distributor load, it's 4 to 5. Okay, so it could be in the range of 4 to 5. And if it is a permanent, if it's a point load, it's going to be 3.5 to 7. So this is a small shop. I can assume a variable action of 4 kilonewton per meter square. Okay, so now I know the variable action acting on the shop or the building or the slab. So let me see uh, uh, the self-weight. So the self-weight, now again code 1 is where you have to find the self-weight. So densities, so densities are given in this code in the annex, so you can see okay, the density, masonry, concrete. So here you can see that concrete densities are given in annex A. So normal weight 24, and it increased by 1 kilonewton per meter cube for normal percentage of reinforcing and pre-stressing steel. So if you have a typical reinforcement, then 24 plus 1, 25. So that 25 kilonewton per meter cube is the density. Kilonewton per meter cube is the density of concrete. So if you assume a slab thickness of 125 millimeter, the slab load, self-weight of the slab is 25 kilonewton per meter cube. So if you take 1 meter cube, say, if you take a 1 meter cube, 1 meter cube concrete, it is 25 meter cube. So our slab is like a part of it, a small fraction of it. It's 0.125. That is my slab thickness. So if you take again one 0.125 thick slab. So you multiply this by 0.125, so that is 25 into 0.125. Let me calculate that. 25 into 0.125, 3.125 kilonewton per meter squared. Okay, so you need to be very careful with that. 3.125 kilonewton per meter squared. So every square meter weighs 3.125 kilonewton. That's what I need, because slab is a two-dimensional element. So I want to see the area load. So area load is going to be 3.125 meter squared. So the self-weight of the slab is known now, and the variable action also known as a area load. And wind action, we have to find from the wind code. I'm not going to touch it now. Earthquake, we are going to find from earthquake code. So if you go through this procedure, so you assume a section, and now you find the load acting on the slab. So the slab load is going to act on this like this on the area excuse me, and that slab transfers the load to the beams. So if you consider a beam, say we have a slab, and say this is our slab. So our beam 1, beam 2, beam 3, beam 4. So depending on the type of the slab, you can determine the loading arrangement of the beam. So there are two types of slabs exist. So the slabs can be one way, two way. As the name indicates, means that in one way slab the load is transferring in one direction. In two way slab the load is transferring in two directions. So if the slab is kind of lengthy slab, so the load on this slab goes to these two beams. So it goes to B1 and B3. B2 and B4 carries no load. B2 and B4 carry no load. So the load is transferred in one direction. So B1 and B3 carry the loads. Okay, and B2 and B4 doesn't carry any load. If it is a two-way, the loads are transferred in both directions. So how that direction is determined, or which, say you have to draw a line 45 degrees, forming an envelope. So these angles are 45. And this area load goes to B1. This area load goes to B2. This area load goes to B3. And this area load goes to B4. And this is depending on the ratio. So if the length to width ratio, so if you consider slab length of the slab, and width of the slab. If the length to width ratio is greater than or equal to 2, then it is one way. else it is two-way. Okay, so if the length to width ratio is greater than 2, greater than equal to 2, then it's one way. If it is less than 2, we consider as two-way slab. So depending on that situation, we can decide. So if you look at our slab, which is a two-way slab, so if you get this area load, you can find the load acting on the beam. So that is the load coming from the slab, and then you have to assume a section for steel, and that section can be verified through the calculation process to see whether it can carry the load. So uh, the classification of the steel sections are depending on the loading. So once you have the approximate load, you can choose a steel section, and then you have to classify that steel. So the steel sections are generally classified into 4 categories. Okay, so we'll see that. We'll see later. A section or element of a member in compression due to an axial load may fail by local buckling. So local buckling can be avoided by limiting the width to thickness ratios of each element of a cross section. So now what happens is, when you use a beam, then part of the beam under compression, part of the beam under tension. When you use a section as a column, the entire section under compression. So this classification is important when it comes to compression. We don't need to classify the steel if it is under tension, but we need to classify if it is under compression. So there are 4 classes. Okay, so class 1, class 2, class 3, class 4. So class 1 means it's a the class 1 is the highest. Now what is the physical meaning is this? Now say you keep loading a beam. Okay, you keep loading a beam. If the beam can develop plastic hinge and sustain the load even after developing plastic hinge, then it is considered class 1. And uh, it's a it's tend to be a less, very less slender type section. So now it's all depending on the this case, this graph. Now if you keep on applying the load on a beam, then the beam will rotate as the moment increases. So rotation means deflection. So it deflects as the moment increase. Moment can be translated to load. So load can be used to determine the moment. So you keep on loading. So here it is the yield position. So if the section can load up to yield, even go beyond yield, this is class 1. So the class 2 can go beyond yield and have plastic hinge formation, but it cannot rotate with plastic hinge. That is class 2. Then if a section can reach up to the elastic level but cannot possess plastic capacity, then it is class 3. And even some sections may not even reach the elastic limit, and they are called class 4. Okay, so Now there are 4 classes, and all depending on how the section behaves. So let me show you. Now you consider a beam, okay, and you know how to find the load and all, and you apply the load. And when you apply the load, the steel will deform. So as you keep on increasing the load, okay, you keep on increasing the load, the it'll take a deformed shape like that. And when you further increase the load, it'll form a hinge here. So there'll be a hinge formation. Okay. So it forms a hinge, but still it's not failing. Means that it's not start rotating fast. That means it didn't lose the capacity. So you keep on loading, it goes slowly down. Okay, so the hinge is forming, but it didn't uh, rupture. Okay, it's still sustaining. So this is called class 1. In class 2, you can load, it will deform and it will form hinge, and this stage will not occur. So once the hinge formed, it will fail. Once the hinge form, it will rotate rapidly. It rotate very fast and lose it will start losing the energy absorbed. That is class 2. Class 3, you can load, it will go up to the yield level. So it will deform like this. It will deform like this without any buckling. So without showing any local effect. So the flange will be intact, the web will be intact, only the hinge form. So class 1, class 2, class 3 can reach the yield stress without any local failure. The local failures, okay, I think you should know that. Let me show you. That is called local buckling. So the local, I mean, the classifications we choose the to determine what kind of buckling you can anticipate. Say uh, there can be 3 type of failures. Okay, if the member under tension, only failure could be failure due to failure due to yield or failure due to rupture. Okay, so before the yielding occurs, suddenly it will rupture because you without you notifying the physical yielding process, it kind of fails. So that is rupture. So there are 2 types of failures you can anticipate. One is uh, yield failure. The other one is rupture failure. Now, if it is under compression, the failure can be due to the material failure due to yield. There is the crushing of the material, or failure due to local buckling. Failure due to global buckling. Okay, so there are two types of buckling failures. Local buckling, global buckling. So what is local buckling? So say I'll show you some images. Local steel columns. Because columns are under compression, so so this is the local buckle. You can see here the flange buckles and the web buckles. So these are local buckles. Say here you can in the beam you can see there is a buckling. This is local buckle. So here you can see there is a buckling. This is local buckling. Okay, so the one plate, the say if you take this steel, there's a top plate, it's a top flange, the middle plate is a web, bottom plate is the bottom flange. The bottom flange buckles because it is under compression. So this is a local buckling failure. And if I look at global buckling, so global buckling is this. So it buckles. Yeah, this is one. Say this is a buckling. Actually, in this buckling, there is no plate buckling, but the entire section is buckling. So there is a element buckling is local buckling, and the section buckling is the global buckling. So three types of failures could occur. So to determine which failure will dominate, we need to know the class. So if you consider the class 1, uh, then the section will not have the local buckling at all because it will keep loading till the hinge forming, and it will further load with forming of a hinge. So class 1, 2, 3. Class 1 can go beyond yield, class 2 can go beyond yield, class 3 can go up to yield. So in these three cases, the local buckling will not occur before it reaches the failure, because the yielding is anyway a failure. So once it started yielding, it will never come back. The deformation will be permanent. Then the class 4 is a section that will never reach the yielding. So means there is a more dangerous section because it can have the buckling before it reaches the uh, yield stage. So we need to do the classification first if we are designing a member which is under under compression load. Okay, so in any section, say with a beam or a column, and if it is an element which has a compression load acting on it, we need to do the classification. So any compression element should be checked for classification. When we do the classification, we do the classification for the plate. So we check for the flange, we check for the web separately, because it is the element failure, not a section failure. Okay, so any compression element should be checked for classification, whether it's a beam or a column. or any other element. And if the member carries only tension all the time, then you don't need to classify them, because we have to do the check differently. So you don't need to do this section classifications. So section classification is the first step of the code. So if I go back to the code, uh, so code 3. So code 3. So if I take the code, so there are several sections in the code. Okay, so there are several sections. So the first part is general section and basis of design and materials, details, and durability. And section 5, structural analysis. Okay. Uh, and under structural analysis, we have the classification of cross sections. So that should be done if you are going to design a member that some way, partially or fully, carries some compressive forces. Okay, so I'll show you the table which can be used. So classification, so there are force classes, and the classification is done using this table. Okay, so this table 5.1, 5.2. Okay, so this is for compression parts. Now, if the part, if the element is subjected to bending, then you have to use this. And if the element is subjected to compression, you have to use this. And if it is subjected to both bending and compression, you have to use this. And this is for flange outstand. So the previous one is for web. So the sheet 1 is for web, sheet 2 is for flange. So you, depending on the plate, you have to choose the appropriate one and classify your sections. Okay, classify your section. Sheet 3 is for angles. Okay, so once you complete the classification, then you can do the checks. So let me let's take a beam, hot roll beam. Say, let me take my favorite section. So this is the section 457, 191, 161. Okay, take this section UKB. So classification of the steel Okay, so uh, classify the steel section 533 sorry 457.191.161 457.191.161, right? 161, yes. UKB, okay, so that is universal beam. So if I want to classify this section 457.191.161, so this is the section, okay. It is a bit deep actually. Let me redraw it. Something like that. Yeah. Because it's a beam, it should possess high I value. So that's why it's deep. So this is 457. So actually it's not 457. So let me take this Tata Steel okay, so Steel for Life. Actually, this is an interactive blue book. It's good to get a PDF. PDF. Steel construction. Anyway, let me take this. So I have my four five seven 191 161. Okay, that's it. So this is my this is my section, and mass is 161.4 kilogram per meter. Depth is 492. So 492 millimeter, and width is 199.4. This width 199.4 millimeter. Okay, then we have the web thickness, blah blah blah. Okay, now we need to find how to determine the uh, how to do the classification. Okay, so let me go to the code. So here we are going to see how to classify it. So it's a beam. So it's a beam means it's partially. Uh, so the beam has two things. It has flange and the web. Okay. So this is for the web. So classification of the web. So here classification of the web. How to classify the web? We need to get the web height and thickness. So here, this is the C over T. So we need to find the C over T ratio. So C over T ratio, if it is less than 72 epsilon, it is it is plus 1. So how to determine the C? So C is obtained, okay? So now class 1 and this C, if you can see, it is between the fillets, okay? The depth between the fillets. So one way to find the C is that you have to say C over T we need to find. So C is equal to its height minus 2 times flange thickness, TF. TF is flange thickness. Say here TF flange thickness. Okay, minus 2R, that is the root radius on both, that is C. Okay, so H minus 2TF minus 2R, and then you divide that by C over T web, you divide that by T web. So here the height is 492 minus 2TF, 2 times thickness of the wave flange is 32, 2 into 32 minus 2 into R is root radius 102, sorry 10.2. Okay, so the root radius 10.2 and that divided by TW. Then this value is 492. So 492 minus 64 minus 20.4. That is 407.6. 407.6 divided by thickness of the web. Now 407.6 is the value given here in the depth between the fillets in the Tata Steel Blue Book as well. So there is a say even in the chart you have the value depth between the fillets, that is 407.6. Okay, 407.6 millimeter, and that is divided by thickness of the web is 18. So 407.6 divided by 18, 407.6 407.6 divided by 18. 22.64. Okay, 22.64. So C over T is 22.64. And if 22.64 less than, okay, what is the code classification is if C over T less than 72 epsilon, then it's class 1. So if it is less than 72 epsilon, class 1. So 72 is a number. Epsilon, what is epsilon? What is epsilon? So epsilon is given here in the code. It is given as Fy over epsilon. I mean, if it is a Fy and the epsilon, say if the Fy, the yield strength of the steel is 235, epsilon is 1. If the yield strength of the steel is 275.92, if it is 355.81. So we will assume if in this question, say we assume classify the C section UKB and steel grade 365. So if I consider steel grade 365, so for 355. So if you consider steel section 355, then my epsilon is 0.81. If I consider steel grade 275, so these 275, 355, 420, 460 all mark the Fy value, that's the yield stress of the steel. So if it's a 355 grade steel, epsilon is 0.81. So the 0.8. So 72 into 0.81 is how much? 72 into 0.81 is 58.32. That is 58.32. So 22.64 anyway less than 58.32. Therefore, a web is a class 1 section. Suppose if it does not satisfy 72 epsilon, we have to go to the next one, 83 epsilon. So then if it is not class 1, it will become class 2. Okay, so that is how you have to decide the classification. So now the web is class 1. That does not mean the entire section is class 1. We have to check the flange as well. So check for flange. Okay, so check for flange. So if you take the flange is different to the web. So if you look at the code, we look for flange outstand. That is the flange that is on one edge it is fixed to the web, on the other edge it's freestanding. So flange outstand C is defined as this. So that is we need to find the C over T. C. So if we find C over T, we can see whether flange also class 1 section. Okay. So CF over TF less than 9 epsilon, then class 1. So C over T less than or equal to 9 epsilon is class 1. Now for the steel, I know it's 355. Epsilon is known. Epsilon is 0.81. So 9 epsilon is 9.81 into 9, 7.29. So if CF over TF less than or equal to 7.29, then it's class 1 section. Okay, so what is CF? Now the CF can be estimated from the, now we know the width 199.4. Okay, so 199.4 is the width of the total I section, then minus web thickness minus T web minus 2R. Okay, so there are two root radiuses. So uh, if you take the total width minus the thickness of the web minus the two root radius, that will give us two flange outstand, both side flange outstand. Then you have to divide that by 2. So that is flange outstand. So 199.4 minus thickness of the web is, thickness of the web is 18 minus 2 root radiuses are 2 into 10.2 divided by 2. So that is 199.4 minus 18 minus 20.4, 161. So 161 divided by 2 is 80.5. So 80.5 is the flange outstand. Then we have to divide CF over TF, thickness of the flange. 80.5 divided by thickness of the flange is, thickness of the flange is 32 here. 32. So 80.5 divided by 32 is 2.52. 2.516. Okay, so CF over TF 2.516. So now here you can see that in the book it's given CF over TF also 2.52. So that is what we got, 2.516. So CF over TF, is it less than 9 epsilon? 9 epsilon is 7.29, so that is less than or equal to 9 epsilon. That is 7.29 epsilon. Hence, flange also class 1. So since both the flange and the web are class 1, we can say the section considered is class 1. Therefore, grade 355 section of 457,191,161. 457 UKB is class 1. Class 1. So the entire section is class 1. So this is what we call classification. Suppose if the flange is class 1 and the web is class 2, then we have to go for the lowest one, that is class 2. So we have to consider the entire section to be class 2 because a plate on that section is class 2. So there are 5 plates in a I section, 1 web and 4 flange outstand. So if the four flange outstand are class 1 and the web is class 1, then the total section is class 1. Okay, so that is how you define the classification. So once you classify for any, once again I repeat, for uh, any bending or compression member, which or any other member that partially or fully experience compression, you have to classify the steel section. You have to. Okay, and if it is under pure tension all the time, you do not need to classify. So the classification is very important. So now say if the for the Fy you have different values for Fy as well. Say in determining the epsilon we have considered Fi. Okay, so say if your section is thickness is less than 16, the thickness of the flange is less than 16, you can consider F5 355. Otherwise 345, it is between 16 and 32. So if you look at the flange, uh, for the flange, uh, the thickness was 32. So it's in this range. Okay, so then it should be 345. If it is for the web, it is 18 millimeters, so again it should be 345. So the yield value varies with the uh, with the with the thickness. So here let me choose this. Now here you can see that in our problem here the thickness of the flange of the web it's 18. So here when finding the epsilon, so the code gives you an epsilon, say the code 355, it gives you an epsilon 0.81 using this equation. So epsilon is square root of 235 over Fy. So epsilon is square root of 235 over Fy. So in this case, if it is 18 millimeter, epsilon is square root of 235 over not 355, but it should be 345. Okay, so 345. So that is 235 square root of, so 235 divided by 345. That is 0.825. So it's 0.83. Okay, so it's 0.825. So we assumed 0.81 here, but it is 0.83 because the Fi also varies with the thickness. Okay, so similarly, you have to consider for the other one as well. So one thing you need to notice that the Fi changes with the thickness of the plate, and that Fi is important in determining epsilon. Epsilon is important in determining the classification. This is only for the classification purpose. Okay. So as a homework, you can try these two sections classification of these two sections and see what kind of classification you obtain. Then uh, we will do these two uh, classifications when we meet on Wednesday morning. So I'll run a small survey so you can choose the classification of these two before we start. So please be prepared with the calculation of the classification. Okay, so let us stop here for today. We have completed one important part of steel design, that is classification of the steel, and also we have seen how to obtain the loads and different kinds of loads. So some basics of structural design plus classification of steel design. So we'll do this one of these two examples when we meet on Wednesday morning. And tomorrow there are no design classes, but the Thursday group will have the design classes, and the follow next week we'll have the same design sections for the Tuesday group as well. So please pass the message, and please try to do this classification before we meet on Wednesday. So let us wind up today's section, and I'll see you on Wednesday.